Welcome everybody. My name is Paweł Strzałkowski. I'm a software engineer at Visuality. And today I'm gonna tell you about fuzzy text search in Ruby. So in other words, how to find something when you don't really know what you're looking for. Let me give you a bit of background. We had a situation. We had a client who has a recruitment company, but they also maintain a job board site. They post job offers. What's going on? Job offers are gathered from the market and posted on this job board site. Job offers include names of the companies that posted them originally. However, they are an employment broker, so they would like to prevent people from applying directly to those companies. So they need to obscure the job offers, make them more anonymous. So a task arises. We need to replace company names with ambiguous the company in job offer descriptions. So we need to take job offer description, a company name, apply some Ruby magic, and well, looks simple, right? Well, if it was that simple, I would just thank you for your attention and move on. However, not so much. The descriptions are handmade, so they contain misspells. Sometimes custom usages of company names with additional punctuation, conjunctions, you name it. So it's not so easy. However, here comes fuzzy text comparison. First of all, what's fuzzy? Fuzzy is something difficult to perceive clearly, something vague, something difficult to understand or explain precisely. So with that term, we go to fuzzy text comparison, which doesn't answer whether two phrases match. It defines their similarity. Fuzzy comparison is a string matrix, measuring the edit distance between two phrases. So in human words, it measures how much does it take to go from one phrase to another. How many edits you have to make to one phrase to get to another one. There's a whole range of similarity metrics measures. We'll be using J.R. Winkler's one. I invite you to Wikipedia to read about all of them because that's pretty interesting. How such a measure work? Let's assume we apply a similarity measure on two phrases. We get a value from 0 to 1. If we get 1, that means that those phrases are exactly equal. If we get 0, they are completely different, and any value in between means, well, some level of difference or similarity. Let's take a look how it looks like in Ruby. We'll be using fuzzy string match-gem, which is a ready library for J.R. Winkler's similarity measure. So I've created a very simple wrapper function, which takes two phrases, sanitizes them a bit. Why? I explain later. So we downcase the phrases, we remove all the white chars, punctuation, and so on, and we send it to this J.R. Winkler's similarity measure, and we round the result to 2 decimal places, just for readability. Let's run it on a few phrases. So let's compare WRUG and JavaScript. As you may see, those phrases have nothing in common, which we all know. However, if we compare WRUG and Ruby, well, there is some level of similarity between those two phrases. If we compare WRUG to WRUG, we get 1, because those phrases are exactly equal. However, let's take a look at a bit more useful cases. If we compare John and Johnny, you see those phrases are almost the same. Their similarity level is almost 1. The same if we compare Gandalf's wife and Gandalf the White, even though there is an additional word in between them. However, the phrases are very similar in fuzzy terms. That still doesn't answer how to find those company names and how to replace them in the job offer descriptions, but let's go there. Let's think how such algorithm should work. So we have to take a piece of text and take a phrase. Find all occurrences of the phrase. This we had covered already by GSAP. However, now we can also find something similar to that phrase. And once we do that, we can replace all the found occurrences with a given substitute. Before we get to the actual algorithm, let's make two assumptions. First of all, how similar something similar is. As I said a second ago, we are going to find similar phrases. But what level of similarity should mean equal for us? If we are looking for a similar phrase, what should interest us? Well, it was kind of a guessing game at the beginning. So I started with something around 08, I think. Then a lot of tests came, a lot of tweaking. The value ended up being 09. So whenever it is said that phrases are equal in fuzzy matching context, it means their Jarrow-Winkler similarity is more than 09. This will be useful later on. Assumption number 2. How long something similar is. If we compare two phrases, one of them can be longer or shorter. Like, let's imagine the company name would be Gandalf White. So Gandalf the White would be something we would be looking for. However, this is longer. So it's not only comparing two words to two words, it's comparing two words to a phrase that might be longer. Again, we have to start with some kind of assumption, but I had quite a lot of materials, like test materials for the algorithm to be prepared for. So after some deliberation, I decided that the matching phrase might be up to 2 words longer. So we would match Gandalf White with Gandalf the Big White, but not with Gandalf and the Big White, in this case. Let's sum up the assumptions. So phrases are equal if their similarity level is more than 09, and matching phrase might be up to 2 words longer than the searched one. Simple enough. Finally, for the algorithm. I'll explain it using a small assignment. So assignment is, take a story, find the name Mary John and replace it with ambiguous the girl, to make it more anonymous. Well, we start the assignment and finish with the story title. We won't go into the content. So the title is Mary as Jane of House Visuality. And there is kind of a problem already. Somebody has taken a wrong Mary and even used some additional middle initial. So now the assignment is take Mary as Jane of House Visuality and find the name Mary John. Let's try. The algorithm has only 3 steps. It's in fact very simple. Let me explain. The first one is break into pieces. We take our text, where we look for a phrase, and break it into pieces. We break it into pieces of 1 word, of 2 words, and so on. What's the largest piece? Well, it's the maximum matching phrase that we defined in the second assumption. So the search phrase is Mary John, which is 2 words long, so the maximal phrase length is 4. This way, we break our text into pieces from 1 word to 4 words. The next step is, I think, quite obvious. Let's just compare all of them to the search phrase. So if we compare Mary John to of House Visuality, well, that's not so similar. Neither is Mary John comparing to Mary S, but it's a bit more similar. Within all the pieces that we've broken the text to, we found 2 equal phrases, equal to Mary John, at least candidates. One is Mary S. Jane of, the second one is Mary S. Jane. And we have to decide which of those are actually going to be returned from the algorithm. Let's take the longer one. We defined its similarity level to be 092. However, in one of the assumptions, we thought about the idea that the searched phrase might be longer, and we defined it might be up to 2 words longer. So we have to predict that the phrases we find might be longer than we need, just as in this case. So for every phrase we found to be equal to our search phrase, we cut a word on the left and we cut the word on the right and check such phrases whether they are more similar or less. So we cut Mary from Mary S. Jane off. We get S. Jane off, which is not that similar. We cut off. We get Mary S. Jane, which is more similar than the initial phrase. So we just found out that the subphrase of Mary S. Jane off is more similar to our Mary John. So at this point, we can completely forget about Mary S. Jane off. We've clearly discovered that that phrase is too long. We'll stay with Mary S. Jane. However, recursively, we are still trying to cut a word on the left on the right to check whether there is something more similar. However, neither S. Jane nor Mary S. are more similar than Mary S. Jane. So the winner is Mary S. Jane. If we apply the algorithm on the sentence Mary S. Jane house visuality, looking for Mary Joan, we'll get Mary S. Jane. Okay. That's a bunch of splitting into arrays, a bunch of similarity checking, but how fast is it? Very simple benchmark. Let's run this algorithm 10 times, divide the execution time by 10, round to 2 decimal places. However, the text now is a bit longer. It's almost 8,000 words long. It's a random text from Wikipedia about NBA. That's why Chicago Bulls and the young player in the search phrase. I've run this algorithm and this benchmark using the first 3 phrases, longer and shorter. However, the execution time stays the same and is quite low. Again, this text is 8,000 words long. The execution time is under a second, well, far under a second, is 140 milliseconds. Once we start to make the search phrase longer, the execution time increases, which is quite obvious because if we have more words in our search phrase, we have to break into more pieces or more combination of pieces. So the execution time increases. However, it's still not that bad. Okay. Whenever you want to tackle such a problem, you will get into similar issues that I have. So let me give you a few tips. First of all, skip characters that make your fuzzy comparison blurry, like harder to perform. For example, punctuation. When I compared company names with company names, and I saw something like Johnston, Peterson, Clark with commas and without commas, for me, for my use case, those phrases were totally equal. So while comparing, I was sanitizing each phrase, removing commas. In your case, Spider-Man might equal Spider-Man because when you will be looking for such phrases, you might not care about white characters. So you might want to sanitize those phrases in these terms again. The next thing is very English specific. Saxon genitives. When you're looking for Superman, in the sentence Superman's powers include, you might want to think that the Saxon genitive, apostrophe S, it's not something that you really want to return. Because, well, in fuzzy terms, this would match, there is no space between those, so the algorithm in general wouldn't cut the apostrophe S. However, you might want to think that that's something that could be handled. Second thing, similarity, at least in the case of this gem, is very fast. This benchmark executes 1 million similarity checks and then divides the result by 1 million just to get an average. And let's assume we compare WRUG and Ruby. That's less than 1 millionth of a second for one comparison. If we extend the phrase, make it a bit longer, well, the execution time, of course, increases. However, it takes the entire alphabet compared to an alphabet in reverse to get to the execution time of 1 millionth of a second. So in general, it's quite fast. That's why it can perform checks for text of several thousand words in under a second. Well, sometimes, I've been talking about sanitization of the phrases. Sometimes you want to skip the white characters, sometimes punctuation. Perhaps there is more. If there is more to be sanitized, you might want to think about a hash table to keep all the results of the similarity checks, just so you don't compare the same phrases over and over again. In this algorithm, when you start cutting words from the left and from the right, you get into situations when you really compare the same phrases over and over again. So such a hash table might come handy. However, when the texts aren't that long, the execution time of the similarity check is so low that for the most part, you don't even need it. And as for the tips, this is my favorite one for this algorithm, test-driven development. You might love it, you might hate it. However, in here, those algorithms are very goal-oriented. When you implement such an algorithm, it's very oriented on your specific goal. So at first you need to define it. Otherwise, you can tweak it for a year and not get anywhere. You have to really write down what you need, exact use cases that you need this algorithm for, because otherwise you really might not get anywhere. I will leave you with one more example. So far we've been working in English, which is quite an easy language. You don't get words in different forms in English. But I can think of at least one other language where there are forms. So let me present you an example in Polish. Again, Wikipedia, a text from Wikipedia about Kapitan America, or in fact, Kapitan Ameryka. In this case, we have Kapitan America in Polish in different shapes and forms. Let's apply the algorithm on this text with the phrase Kapitan America to be looked for. As you can see, the algorithm, even though it knows nothing about Polish, especially it was tweaked for English with those Saxon genitives, however, it's still able to find all the usages of Kapitan America or phrases related to that within this text. Thank you very much for your attention. Perhaps there are questions.
Yeah. Going back to algorithm, when you decide which phrase you should use you should replace. Why you didn't choose to decide it based on the high score?
Because it might be the case that you might need both, in fact. Because the text might be long. Let's say you have two usages. One is AB, word A and word B, and the other one ABC, but they both match. Mm-hmm. It's not that you are sure you can get rid of one. It might be the case that you need both. I hear that I'm not really answering your question. Okay, because you assume that I had both of the phrases already when I started. Yeah, there were two equal phrases in this one. Mm-hmm. Let's assume we have 200. And you have to compare all the strings, all the phrases between each other, checking whether perhaps one is a suffix of other one, and then decide on the score. In fact, this is exactly what I'm doing. I just used this approach. I'm not comparing strings, taking pieces, let's say, of an array, one by one. I've just used this representation because it's easier for me just to think about. But it would be the same as taking an array of phrases and comparing one by one. I think this is, more efficient and more structured, I think, for my mind.
Thank you.
Thank you very much.